Hi folks, continuing with our discussion on inductance. I'll remind us of the definition for mutual and self. Well, d phi into from 1 by dt divided by d I in 1 by dt is equal to the mutual inductance, or you could simply say the mutual inductance is equal to phi into from 1 divided by I in 1. And by the same token, you say that phi in whatever divided by I in that same, from the same, because you have a solenoid, phi divided by I is equal to L. Okay? Okay. So, let's talk about, let's say you have a solenoid here, okay? And you have, I think there might have been issue in a previous slide with, I think we're good. Okay, so you have current I coming through here, okay? And it creates a magnetic field, let's say, in there. And you want to get an idea about the energy stored in there. So what is the energy stored in magnetic fields? So let's just talk about, we have now the epsilon induced is equal to L di by dt. Okay? So so now the power is equal to delta V times I. In this case, it's epsilon I. So that's equal to L I di by dt. Let's say we want the energy stored. Energy is the power. Well, the amount of energy stored in a U magnetic is equal to the integral of P. Integral of P dt. Okay, and let's say we're going from t1 to t2, or from time equals 0 to t. That becomes the integral of L I di by dt times dt, and dt's cancel, so that becomes the integral of, so the energy stored is equal to L times I times di, and that's, let's say, go from current 0 to current I, and that becomes 1/2 L I squared. Okay. Now let's talk about the energy density. What is energy density? So this is the energy in an inductor, okay? The energy density, okay? So the energy density is, well, energy density, okay, in this solenoid is equal to the energy magnetic divided by the volume, and that's equal to, well, try to come up with an expression for this on your own. Right? Pause this video for a minute and try to come up with an expression for the energy density in an inductor. Right? We have the conductor has area A and length L. You have an expression for the inductance of an inductor already. What would the energy density be? The energy is 1/2 L, and this is volume, right? Okay, so the energy volume density, 1/2 Li squared divided by A times L, okay? And we know from our discussion on the calculation of the inductance of an inductor or a solenoid, this is equal to 1/2 L is equal to mu naught times N squared times A times L divided by A times L, and that becomes equal to, and you have I squared, right? and that becomes equal to, what is the field? So AL cancels with AL, and mu naught Ni is equal to, remember that mu naught, the magnetic field inside an inductor, is equal to mu naught Ni. So you can see from here that this becomes 1/2 b squared over mu naught, or b squared over 2 mu naught. There is another expression for this in terms of H as well. Look that up. We won't be getting into this discussion, but you can say now that the energy density stored in magnetic fields is equal to b squared over 2 mu naught. And if you want to find the energy in any assortment where there is a magnetic field, B, you can now say that the energy is equal to the integral over the volume that we're looking at of triple integral b squared over 2 mu naught. You can also, again, what I'm asking you to do is find an expression for this in terms of the dot product of B and H. Pretty simple. Should be, should be able to figure that out. Again, we're not testing you on this. I just want you to think that this can be expressed in terms of B and H as well. This relates to the energy density in a capacitor, which we did not really discuss, but it's a good point to bring it up right now. So in a capacitor, the energy is given by, let's say we take a parallel plate capacitor, the energy was given by 1/2 C, if you want, times C times delta V squared. Okay, let's say we write it this way. So that's the energy stored in the capacitor. And if I want the energy density, and this capacitor has separation D, plate separation D, and plate area A, we see that the energy density is given by 1/2 C for a parallel plate capacitor is epsilon naught A over D multiplied by delta V squared is E squared times D squared, and divided by the volume, which is equal to D times A. These cancel, these cancel. You see that this is equal to 1/2 epsilon naught E squared. If you have a material, if you have a material in there, like if you have a dielectric in there, this becomes equal to 1/2 epsilon E squared, and that can always be written as 1/2 into D dot E. So this is an expression for the energy density in an electric field, not just in a capacitor. We're starting with a capacitor to come up with an expression for the energy density in electric field. The derivation we did for the solenoid looks at a field that is straight inside the solenoid. But when you look at energy density, small volumes or small segments in space, you can use this expression and the expression we derived earlier, to you can call whatever you have, if it's locally flat, you look at the energy density over a small area, you can approximate things to be flat there as well, and that expression actually can be used to derive the energy in a given volume. This is not just the energy in a capacitor, this is the energy density. What we just derived before for the magnetic field was the energy density stored in a magnetic field. You can use that expression to find the energy density. If you have the expression for the field, you can field over, the field is changing in space or whatever, you can use that expression to find the energy stored in that space in the magnetic field in that space, and you could use this expression to find the energy stored in the region where there is an electric field as well. Another point of similarity to look at now that we have talked about magnetic dipoles as well is the relationship between the torque on a dipole is equal to mu cross B, okay? And there is similarities between this and the torque from an electric field on a electric dipole. So basically, if you have a current loop, okay, and the current is going this way, and you put this in a magnetic field like that, right? This magnetic field will exert a torque on that loop, and that discussion is done elsewhere in videos as well. And you know what this loop will want to do is line up with the magnetic field, so that the magnetic dipole from this area loop has area A and current I flowing in it. The magnetic dipole moment is mu this way, right? And mu is equal to IA, if you will, and the direction of the magnetic dipole is, so you have B external, right? And you have the current flowing in the loop, creating a magnetic field in the loop, right? This is B from the loop itself, right? And the magnetic field, the external magnetic field, will exert a torque on the loop given by mu cross B, and we've seen the details of that elsewhere earlier in other videos that I posted for you. Now the direction of the dipole moment is given by, dipole moment due to the loop is given by the direction of the magnetic field due to the loop at the center of the loop. So you follow the right hand rule like this, and that gives you that B loop is pointing this way and that mu is in the same direction. Another expression I'd like you to consider is that the energy stored in a when you bring this, okay, let's say you have this loop was lined up with the field and you brought it this way now, right? You brought it this way, it takes energy to do so, and the energy stored is equal to minus mu dot B. There are similar expressions that I took up with you in class for an electric dipole sitting in an electric field, how it wants to line up with the field, and if you want to twist it away from the field is pointing this way, dipole is this way, you want to twist it in the field, it takes torque to do so, and the torque was equal to P cross E, and also the energy, look up the energy stored as you try to do that. You store energy in the, in that dipole. I'll leave this to you. I want you to look this up, to try to find it on your own. You've got a dipole and electric field. What is the energy stored when you twist it, okay, in the field, okay? Anyhow, cool. Yeah. All right, let's pause this for a sec.